You have never been still, not for 1 second of your life. The floor under your bed is outrunning a passenger jet carried around the spine of a spinning planet. The planet is falling around its star at 30 kilometers every second. The star is being hauled around a galaxy by matter nobody has ever seen, and the galaxy itself, every star you have ever looked at, is streaming toward a single marked point behind the dust of the southern sky, at 1.4 million miles per hour, pushed from behind by an emptiness 500 million light-years wide. Astronomers know the speed, they know the direction. They have known since the 1970s. What they could not see for decades was the destination itself, hidden behind the one band of sky our own galaxy refuses to let us look through. By the end of tonight, you will know exactly where everything is going, and the final answer is not a place at all. Get comfortable. If this is how you like to fall asleep, riding a current you cannot feel, toward a place you cannot see, a quick like and subscribe genuinely helps this channel reach more curious minds like you. Because by the end of this, you will never look at a quiet room the same way again. Now let's gently drift into this. There is a glass of water somewhere near you right now. Maybe it is on the nightstand, maybe on a desk across the room. Look at the surface of it. The water is perfectly level, perfectly quiet. Nothing about it suggests that the glass, the table, the room, and you're all aboard something in motion. And that quietness is not a trick. It is a real measurement, made by a real instrument. Water is an honest witness. If the room were accelerating, the surface would tilt. If the room were shaking, it would shiver. The water reports, truthfully, that nothing here is being pushed. And yet the water is wrong about something, in a way that took our species most of its history to understand. Because the room is moving. It has never once stopped moving, and neither have you. Start with the ground itself. The Earth turns on its axis once a day, and unless you are standing on one of the 2 geographic poles, that rotation is carrying you sideways through space right now. At the equator, the ground moves at about 1,670 kilometers per hour, which is faster than the speed of sound. At the middle latitudes, where most of humanity actually lives, the pace is closer to 1,000 kilometers per hour. To put that number somewhere, you can feel it. A commercial airliner at full cruise covers around 900 kilometers in an hour. The floor beneath your bed is outrunning a jet, and it has been doing so every hour of your life. Over an 80-year lifetime, which works out to about 700,000 hours, the spin of the planet alone carries a human body roughly 1 billion kilometers. You will travel 1 billion kilometers without ever buying a ticket, most of it while doing absolutely nothing, a good portion of it while asleep, and the spin is the smallest rung on the ladder. The Earth also orbits the Sun, and it does so at an average of 30 kilometers every second. Not every hour, every second. In the time it took you to read that sentence, you moved about 100 kilometers. Over a year, the planet traces a loop nearly 1 billion kilometers around, and over that same 80-year life, the orbit adds about 80 billion kilometers to your personal odometer. Almost all of it, admittedly, in a circle. You keep coming back to the same neighborhood of space each year, the way a horse on a carousel keeps returning to the same painted post. But the speed is real, and you feel none of it. Then the carousel itself is moving. The Sun, carrying the Earth and every other planet, asteroid and comet in its household, is orbiting the center of the Milky Way galaxy at about 230 kilometers per second. That is more than 7 times faster than the Earth circles the Sun. One full lap around the galaxy takes somewhere between 225 and 230 million years. The last time the solar system was in this part of its orbit, the dinosaurs were just getting started. The Sun has completed roughly 20 of these laps in its lifetime, 20 circuits of a wheel so large that the entire recorded history of our species does not register as a rounding error on a single one of them. So the honest picture, before we go any further, looks like this. You're on a spinning ball, which is circling a star, which is circling the center of a galaxy, and every layer of that motion is silent, smooth, and completely undetectable from where you're lying. Our galaxy is like a tiny raft adrift on an ocean at night, with no moon and no lighthouse, and we are passengers below deck, feeling nothing, watching the water in a glass sit perfectly still. And here is where the story stops being a list of orbits and becomes a mystery. Because in the 1970s, astronomers discovered that the raft is not just drifting, it is being pulled. Two lines of evidence surfaced at almost the same time from two completely different directions. The first came from astronomers doing something that sounds almost bureaucratic, taking a census. R. Brent Tully and J. Richard Fisher were surveying galaxies beyond our own, using radio telescopes, including the Parkes dish in Australia, to measure not just where our galactic neighbours sit, but how they move. This was slow, patient, unglamorous work. A galaxy does not announce its velocity. You have to coax it out of faint shifts in radio light, one galaxy at a time, and then assemble hundreds of those measurements into something like a weather map of the local universe. When Tully and Fisher and the astronomers who followed them stepped back and looked at that map, something odd emerged. The galaxies around us were not drifting at random, each on its own errand. Their motions shared a common focus. Roughly speaking, they were all leaning the same way, like grass bent by a wind nobody could feel, like boats in a harbour all straining against their moorings toward the same stretch of open water. The second line of evidence came from the sky itself, from the oldest light there is. The universe is filled, in every direction, with a faint bath of microwave radiation left over from its hot early years, a relic from the era just after the Big Bang. We will spend real time with this light later in the video, because it turns out to be one of the most important measuring instruments ever found. For now, what matters is this. When astronomers in the 1970s measured that ancient radiation carefully across the whole sky, they found it was not quite even. It was slightly warmer in one direction of the sky, and slightly cooler in the exact opposite direction, in a pattern that motion would produce. Some of that lopsidedness was easy to explain, because the Sun is orbiting the centre of the galaxy, and that orbital motion should tilt the measurement, and it does. But when the astronomers subtracted the Sun's orbit, expecting the lopsidedness to vanish, it did not vanish. A residue remained, an extra motion, amounting to hundreds of kilometres per second, that no known orbit accounted for. The entire Milky Way, along with its neighbours, was moving in a direction it had no obvious reason to be moving, at a speed nothing visible could explain. Two different methods, two different instruments, two different teams. One conclusion: our galaxy, and thousands of galaxies around it, are being drawn toward a particular place, a specific location in the universe, as if tied to it by invisible cables tens of millions of light-years long. Naturally, the astronomers turned their telescopes toward that place, to see what could possibly be doing the pulling. And this is the detail that turns the discovery into something almost cruel. The direction of the pull happens to lie behind the one region of sky we cannot see through. The flat disk of our own galaxy is thick with gas and dust, and from our position inside it, that dust forms a band across the heavens that swallows the light of whatever sits beyond. Astronomers call that band the zone of avoidance, and the name is older than the mystery. In the 1800s, sky mappers noticed that the faint smudges they were cataloguing seemed to avoid the band of the Milky Way, and only later did anyone realise the smudges were distant galaxies, and they were not avoiding anything. Our own house was blocking the view. The dust in our galactic backyard hides whatever we are falling toward, the way the glare on a windshield hides the road. So for decades, the situation stood like this. We knew we were moving. We knew how fast, to reasonable precision. We even knew the direction and could point to it, a patch of southern sky toward the constellations Centaurus and Norma. What we could not do was see the destination. We could not map it. We could not weigh it. We could not name what it was because nobody had ever laid eyes on it. So astronomers did the only thing left. They named the mystery itself. They called it the Great Attractor, a persistent sink of gravity, a point in the cosmos that pulls and pulls and pulls and does not say what it is. Our entire galaxy, home to hundreds of billions of stars plus thousands of other galaxies, each with their own hundreds of billions, all drawn toward it like moths toward a porch light none of them can see. That phrase, the Great Attractor, is one of the most honest names in all of science, because it describes an effect while admitting total ignorance of the cause, and it raises the question that this entire video exists to answer. It is a question a child could ask, and it is the question the water glass has been quietly hiding from you your whole life. If nothing is still, if the ground and the star and the galaxy and the neighbourhood of galaxies are all in motion, all of it silent, all of it unfelt, then there is really only one thing left to ask. Where is everything going? By the end of tonight, you will have the real answer. It comes in 3 layers, and I will tell you now that the last layer is not what you expect. It is stranger than a hidden mass, stranger than a collision, stranger than anything sitting behind the dust. But we cannot go there yet, because before you can ask where everything is going, you have to face an older and more uncomfortable question first, one that nearly strangled astronomy in its crib. The question of how you could possibly know that anything is moving at all. It sounds simple. It defeated some of the greatest minds who ever lived, and the answer begins with a dying man and a book he waited his whole life to release. In the spring of 1543, in a room in northern Poland, an old church official lay dying of a stroke. His name was Nicholas Copernicus, and according to the story passed down by his friends, a printed copy of his life's work was placed in his hands on the day he died. The book was called On the Revolutions of the Heavenly Spheres, and he had delayed publishing it for decades because he understood exactly what it was going to do. Inside that book, the Earth moves, and the moment the Earth moves, a problem is born that will take 400 years to solve, a problem that leads directly to the question we are chasing tonight. Because before you can ask where everything is going, you have to establish something that sounds absurdly simple and is not simple at all. You have to prove that anything is going anywhere. Consider how the universe looked before that book. For thousands of years, the brightest minds in Europe and the Middle East agreed on the basic architecture of reality. The Earth sits perfectly still at the centre, and everything else wheels around it. And it is worth saying clearly that this was not a stupid idea. It was the obvious reading of the evidence. The ground feels utterly stationary, and the sky visibly turns. The ancient astronomers built a machinery of mathematics on that foundation, a system of circles riding on other circles, some centred on the Earth, some centred on empty points in space. Each planet carried on its own nest of wheels. The system was ungainly, a mathematical contraption held together with exceptions. But here is the uncomfortable truth. It worked. It predicted eclipses. It tracked the planets well enough to navigate by. A theory can be deeply wrong and still pass its exams for 2,000 years. That is one of the most unsettling lessons in the history of knowledge, and it is worth keeping beside you all night, because it will come back near the end of this video wearing a different face. Copernicus proposed a renovation. Put the sun at the centre, motionless, and set the Earth circling it along with the other planets. In some ways, his system was scarcely tidier than the old one. He still needed his own collection of circles to make the predictions come out, but the philosophical price of the book was enormous, because a moving Earth immediately raises objections that any farmer could state and no philosopher could answer. If the Earth is racing around the sun, why do we not feel a permanent hurricane? When you ride a horse, wind hits your face. When you run, the air pushes back. The Earth's orbital speed, we now know, is 30 kilometers per second. Where is the wind? And if the ground beneath Poland is swinging around the planet's axis at hundreds of kilometers per hour, why is anything still attached to it? Why are cathedrals and cattle and coastlines not flung off into the void like mud from a spinning wheel? The stillness of the water glass from the beginning of tonight is not a small observation. For centuries, it was the single best argument that the Earth could not possibly be moving. The first crack in that argument came from Galileo, and he made it with a thought experiment set below the deck of a ship. Shut yourself in a windowless cabin, he said, on a ship gliding across smooth water at a steady speed. Fill a bowl with water and watch it. Let flies loose in the cabin and watch them. Drop a ball and watch where it lands. Nothing you can do in that cabin, no experiment with water or insects or falling objects, will tell you whether the ship is moving or tied up at the dock. The water sits level either way. The flies drift in every direction with equal ease either way. Motion that is shared, perfectly and smoothly, is motion that is erased. The passengers move with the ship, the air in the cabin moves with the ship, and so the ship's speed simply vanishes from every local measurement. And that is the answer to the farmer's objection. We do not feel the Earth's orbit because everything we could measure it against, the air, the oceans, our own bodies, is riding along with us at exactly the same speed. There is no headwind, because the atmosphere is a passenger too. Newton took Galileo's insight and built it into the foundations of his physics. Uniform motion is undetectable from inside. But Newton could not quite let go of the old stillness. He believed that beneath all the relative motions there existed an absolute space, a fixed, universal stage, God's own reference frame, against which everything's true motion could in principle be scored. He even had an argument for it. Take a bucket of water and spin it. At first the bucket turns and the water lags behind, its surface flat. Then the water catches up, spinning with the bucket, and its surface curves into a bowl shape, climbing the walls. Here is the puzzle. When the water's surface is curved, the water is not moving relative to the bucket. They are turning together. So what exactly is the water spinning relative to? Newton's answer was relative to space itself. The curved surface of the water, he argued, is the universe telling you about absolute motion. It was a serious argument, and it stood for 2 centuries. But absolute space, if it exists, should be detectable. And when instruments finally became sensitive enough to look for it, the universe declined to cooperate. In 1887, in Cleveland, Ohio, Albert Michelson and Edward Morley built one of the most precise instruments of their century, an arrangement of mirrors and split beams of light, designed to detect the Earth's motion through the invisible medium that light was believed to travel in. The idea was straightforward. As the Earth swings around the Sun at 30 kilometers per second, a current of that medium should blow past us, and light should travel at slightly different speeds along the current versus across it. The instrument was sensitive enough to see the effect clearly. It saw nothing. They rotated the apparatus. Nothing. They waited 6 months for the Earth to swing around the Sun and race the opposite direction. Nothing. It is often called the most famous failed experiment in the history of physics, and its failure was a message. There is no current, no medium, no absolute rest frame hiding underneath things, no cosmic dockside against which the ship's true speed is written. It took an Einstein to accept what that meant. In his relativity, the rule Galileo found in the ship's cabin is promoted to a law of the universe. All uniform motion is relative, full stop. There is no absolute ruler, no privileged stillness anywhere. Picture 2 spacecraft coasting past each other in empty space, engines off. The pilot of the first may declare, "I am at rest," and that other ship is doing the moving. The pilot of the second has every right to say precisely the reverse, and here is the part that refuses to sit comfortably in a human mind. They are both correct, completely, permanently, equally correct. The question of which one is really moving has no answer, not because we lack the instruments, but because the universe does not contain the fact. From this single idea, the rest of relativity unfolds, the melting of space and time into one fabric, the equivalence of mass and energy, the speed limit of light. But tonight we only need the first brick. Uniform motion is not a property an object has. It is a relationship between 2 things, nothing more. There is one loophole, one kind of motion the universe does score absolutely, and you should know about it because it explains how we can be sure of anything at all. Rotation. Spinning is not uniform motion, it is continuous acceleration, a perpetual changing of direction, and acceleration announces itself. This is why Newton's bucket water climbed the walls, and it is why the Earth's rotation, unlike its journey through space, can be proven without ever looking at the sky. Every hurricane is proof. Air rushing toward a low-pressure zone gets deflected sideways by the planet's spin, twisted counterclockwise north of the equator and clockwise south of it, a signature written into every storm system on Earth. In 1851, Léon Foucault hung a heavy pendulum from the dome of the Pantheon in Paris and let it swing, and over the hours, the plane of its swing slowly rotated as the planet turned beneath it. That pendulum is still a museum exhibit today, in lobbies all over the world, and it is worth pausing on what it actually is, an indoor instrument, requiring no window, no telescope, no star that measures the turning of a planet. Even under a permanently overcast sky, we would know the Earth spins. But now feel the weight of the trap that closes at this point in the story. Rotation, we can prove from inside. Travel, we cannot. And the question we set out to answer tonight, where is everything going, is a question about travel, about the voyage of the whole galaxy through the universe. Einstein seems to have slammed that door permanently. If all uniform motion is relative, then saying the Milky Way moves at 600 kilometers per second is exactly as valid as saying the Milky Way is perfectly still and the rest of the universe is streaming past us. Both descriptions are legal. Neither is truer than the other. The question "where are we going" starts to look like it is not merely unanswered, but meaningless, a sentence with the grammar of a question and no content inside, and it would be meaningless in an eternal, unchanging cosmos. It is not meaningless in ours. Because our universe, it turns out, is not the fixed stage Newton imagined or the featureless emptiness Einstein's ships coast through. Our universe is doing something. It is expanding. And a universe that expands, a universe with a history, keeps something no static universe could ever have. It keeps a record. The universe has a memory of its own past, written in light, spread across the entire sky, and pinned to the one moment everything glowed. We have met this light once already tonight. Now it is time to read it. Somewhere in your home, there may still be an old radio, and if you tune it between stations, a fraction of the hiss coming out of the speaker is not interference from power lines or distant thunderstorms. About 1% of that static, on an old analog set, is the universe itself. It is radiation that has been travelling since before there were stars, and it is passing through your bedroom right now, in every direction, at all hours. Tonight, that hiss is going to answer a question that Einstein's relativity seemed to have made unanswerable. It is going to tell us, in defiance of everything the last part established, exactly how fast we are moving and exactly where we are headed. Here is the loophole. Relativity says that no experiment inside a sealed cabin can reveal uniform motion, and that remains true. But our cabin has windows, and the universe outside the windows is not a featureless void. It is a universe with a direction of development, a universe in the middle of doing something. On the larger scales, every distant galaxy is receding from every other, not because they are all fleeing some central point, but because the space between them is stretching. The universe was smaller yesterday than it is today, and it will be larger tomorrow. That sounds like a statement about geography. It is actually a statement about time. An expanding universe has a history, a preferred direction of change, and that history quietly restores something Einstein's empty space lacked, a natural frame of reference. Not an absolute stage in Newton's sense, but something almost as useful. There is one special way to move at every point in the cosmos, the way that simply rides along with the expansion, the way that sees the universe unfolding evenly on all sides. Call it going with the flow. An observer moving with the flow sees the same recession of galaxies at the same rate in every direction. An observer moving against the flow, even slightly, sees the universe lopsided. That gives cosmologists a clean and beautiful definition. Take any object, a star, a galaxy, a cluster of galaxies. Subtract the universal expansion from its motion. Whatever is left over, whatever deviation remains from the pure outward flow, is called the object's peculiar velocity. Peculiar, here, in the old sense of the word, not strange but particular, belonging to that object alone. Peculiar velocity is the honest motion of a thing, its private travel through the universe, and it is never random decoration. Peculiar velocity is the fingerprint of gravity. Where matter has gathered, it pulls, and things fall toward it, and those falls, measured in tens or hundreds or thousands of kilometers per second, are the peculiar velocities. Map them, and you are mapping the hidden terrain of the cosmos, every slope and basin of it. But a definition is not a measurement. To actually measure our own peculiar velocity, we would need to somehow photograph the flow itself, to catch the universe's rest frame in the act of being at rest. And this is where the story collides with one of the luckiest facts in all of science. The universe took that photograph for us, 380,000 years after it began, and copies of it are still arriving from every direction, including into the static of that old radio. Rewind to that era. The entire universe is filled with a glowing fog, a plasma hotter than the surface of a star, so dense with free electrons that light cannot travel in a straight line. Every ray is scattered within a fraction of a second of being emitted. The cosmos is opaque, a wall of light in every direction. Then, as expansion cools the plasma below a critical temperature, roughly 3,000 degrees, the electrons are captured into atoms, and the fog clears everywhere in a window of only about 10,000 years. Cosmically speaking, that is a camera flash, and the light that was in flight at that moment is suddenly free. It has been flying ever since, stretched by the expansion of space from a hot glow into cool microwaves, and it is called the cosmic microwave background. It is, by an overwhelming margin, the majority of all the light in the universe. For every particle of starlight, there are roughly 1 billion particles of this ancient light. Every cubic centimetre of space, including the ones inside your body right now, holds about 400 of these fossil photons. You cannot leave it. There is nowhere in the universe to go where the flash is not arriving. Two properties make this light the perfect witness. First, as we said, it comes from everywhere, emitted by every region of the early universe at essentially the same moment, so it carries no local bias, no allegiance to any galaxy or cluster. Second, it is almost unbelievably uniform. Measure its temperature in one patch of sky, 2.725 degrees above absolute zero. Measure it in the opposite patch, the same to about 1 part in 100,000. The early universe was smoother than any surface humanity has ever manufactured, and its afterglow inherited that smoothness. And a perfectly smooth, perfectly universal bath of light is exactly the thing relativity said we could never have. A reference. Not a wall to push against, but a sea to measure our wake in. If you are at rest with respect to the expansion, the ancient light arrives with equal intensity and equal temperature from all sides. But if you're moving through it, simple physics takes over, the same physics that changes the pitch of a passing siren. The light ahead of you gets compressed, shifted warmer. The light behind you gets stretched, shifted cooler. Your motion prints itself onto the whole sky as a gentle gradient, warm in front, cool behind, and the size of that gradient is your speedometer. Cosmologists call the pattern a dipole. You can think of it as a bow wave, the crease a moving boat makes in still water. The universe's oldest light doubles as the universe's speed trap, and there is no talking your way out of this one because the radar has been running for 13.8 billion years. In the 1970s, instruments finally became sensitive enough to check us. Some of the decisive measurements were made from a U-2 spy plane, flying at the edge of the atmosphere with a microwave radiometer where the cameras used to go. And the verdict came back: we are speeding. The sky is warmer than average in the direction of the constellation Leo and cooler by the same amount toward Aquarius on the exact opposite side. The difference is tiny, about 3.5 thousandths of 1 degree, but it is unmistakable, and it has been confirmed by every satellite and balloon and mountaintop instrument since. Translated into velocity, the Sun and everything travelling with it is moving through the ancient light at about 370 kilometers per second. That is over 800,000 miles per hour, and unlike every other speed we have discussed tonight, this one is not relative to a neighbour, not relative to a star or a galaxy that might itself be moving. It is our speed relative to the universe's own frame, the closest thing to an absolute velocity that nature permits. There is even a built-in honesty check, a way to be sure this pattern really is our motion, and not some intrinsic stain on the sky. As the Earth circles the Sun, our velocity changes by 30 kilometers per second, first added to the Sun's motion, then subtracted every year, and the dipole wobbles in perfect time with it, growing and shrinking by exactly the predicted amount, an annual heartbeat in the oldest light there is. The sky itself confirms every 12 months that we are the ones moving. Now do what the astronomers of the 1970s did. Peel the onion, start with 370 kilometers per second and subtract the Sun's orbit around the galactic center, the same 230 kilometers per second we met at the start of tonight, pointed in its own particular direction. Then account for the motion of our galaxy within its little family of neighbors, a family we will properly meet later tonight. What remains, after every local orbit is stripped away, is the true, private, peculiar velocity of our entire galactic household through the universe. It comes out to roughly 600 kilometers per second, about 1.4 million miles per hour. Not spin, not orbit, not any closed loop that returns to its starting point. Travel, actual displacement through the cosmos, in a definite direction that has been going on for billions of years, and the direction is the part that should make the hair on your arms rise. The warm patch of the dipole, corrected for all our local orbits, points toward the southern sky, toward the border of the constellations Centaurus and Hydra. It points, within a few degrees, at the exact patch of obscured, dust-blotted heaven where Tully and Fisher's galaxy maps found every neighbour leaning. Two completely independent witnesses, a census of galaxies and the oldest light in existence, aim their arrows at the same hidden spot behind the zone of avoidance. The speed trap and the harbour charts agree. We are doing 1.4 million miles per hour and we have a bearing. What we do not yet have is any understanding of what we are or what is riding with us. Before we chase that bearing to its source, we need to take stock of the vehicle. Because the thing making this journey is not the Earth and not even the Sun. It is something much larger, and the next rung of the ladder reveals a passenger list and a piece of luggage that nobody expected. Picture an odometer for your body, a small counter installed at the moment of your birth, ticking upward with every kilometre you actually travel through space. Not the kilometres you drive or fly, the real ones. By the time you finish watching this video, that counter will have advanced by more than 1,000,000 kilometres. By your 80th birthday, the digits are almost beyond reading, and what makes the counter worth imagining is not the total. It is the fact that almost every kilometre on it was covered while you believed, with complete sincerity, that you were sitting still. Before we chase the bearing we found in the last part, let us read the odometer honestly, rung by rung, and meet the vehicle that is actually carrying us. Because the vehicle has a secret, and the secret is heavier than everything we can see, combined. Rung 1, the spin. Depending on where you live, the turning Earth carries you between 0 and 1,670 kilometers per hour. Stand on the geographic pole, and you merely pivot in place, once per day, like a figure skater at the end of a routine. Stand in the middle latitudes and you cover about 1,000 kilometers every hour. Over an 80-year life, that is on the order of 1 billion kilometers of travel, purchased entirely by the accident of being born on a rotating ball. 1 billion kilometers is roughly the distance from the Sun to Saturn. You will commute to Saturn in your sleep. Rung 2, the orbit. The Earth circles the Sun at an average of 30 kilometers per second, and the honest picture of that motion is free fall. The planet is perpetually falling toward the Sun, and perpetually missing, the way a thrown ball would circle forever if only it were thrown fast enough and there were no air. 30 kilometers per second, sustained for a lifetime, adds about 80 billion kilometers to the odometer. But notice what kind of travel this is. It is a loop. Every January you're back in roughly the same stretch of space as last January. Enormous mileage, zero destination, a commuter's orbit in the most literal sense. Rung 3 is where the numbers stop being about circles around home and start being about a genuine voyage. The Sun, hauling its entire household along, orbits the centre of the Milky Way at about 230 kilometers per second, one lap every 225 to 230 million years. Since the Sun formed, it has made about 20 circuits, and it was this rung, this ordinary-sounding orbital statistic, that handed astronomy one of the greatest shocks of the 20th century. Because you can audit an orbit. The speed of a circling body tells you how much mass must be inside its orbit, holding it. That is not a guess. It is the same arithmetic that weighs the Sun using the Earth's orbit, and it does not negotiate. So astronomers added up everything visible inside the Sun's orbit, every star that shines, every cloud of glowing gas, and then, being careful people, they padded the estimate generously for all the dim stars and cold clouds they might have missed. The audit failed anyway, and it did not fail by a rounding error. At 230 kilometers per second, the Sun is moving far too fast for the visible mass of the galaxy to keep it. By everything we can see, the Milky Way should have lost its grip on the Sun billions of years ago, and our star should be sailing off alone into intergalactic darkness, planets in tow, a runaway. And yet the Sun is still here, 20 laps and counting held in its lane, lap after lap, by the gravity of something that does not shine. Astronomers call it dark matter, and the name, like the Great Attractor, is an honest confession dressed as a label. Whatever it does not emit light, does not reflect it, does not block it. It reveals itself only by its pull, and there is no small amount of it. To hold the Sun and every other star in the galaxy's grip, the Milky Way must be wrapped in an invisible envelope containing several times more mass than all of its stars and gas together. Hold that thought against your skin for a moment. The galaxy you have seen in photographs, the shining disk, the spiral arms, the hundreds of billions of stars, is the minority of the object, a dusting of lights on a body of darkness. When we ask where everything is going, the everything is mostly a thing no one has ever seen. This is the first invisible hand in tonight's story, an unseen mass that steers the visible universe. Keep it in mind, because in the final act of this video a second invisible hand will appear, and it does not steer. It does something far stranger. There are two smaller motions worth adding to the ladder, not because they change the totals much, but because they change the picture of what kind of thing we are riding. First, the Sun does not glide around the galaxy on a flat, dignified track. As it orbits, it also drifts up and down through the galactic disk, rising a few hundred light-years above the midplane, slowing, sinking back through, and dropping below over and over on a cycle tens of millions of years long. The galaxy's disk is not a floor, it is a sea, and the Sun is a buoy, bobbing as it travels, lifted and lowered by the combined gravity of the disk itself. Every crossing of the midplane takes us through the densest lanes of the disk's gas and dust, and some researchers have wondered aloud whether those crossings correlate with anything in Earth's distant past, with comet showers shaken loose or climate shifts recorded in stone. Nothing there is settled science, and we will not pretend otherwise tonight. What is settled is the bobbing itself. Your address in the galaxy has a vertical coordinate, and it is changing right now. Second, the neighbourhood we happen to be sailing through is a crime scene. The solar system is currently crossing a region called the local bubble, a cavern hollowed out of the galaxy's interstellar gas, roughly 1,000 light-years across. Its walls are the swept-up wreckage, and its interior is emptiness even by the standards of space. The gas inside the bubble is thinned to less than 1/10 of the galaxy's usual density, and the ordinary interstellar medium is already so sparse, roughly 1 atom per cubic centimetre, that it would count as a flawless vacuum in any laboratory on Earth. What excavated a cavern 1,000 light-years wide? Supernovas, a series of massive stars living and dying in this region over the past 10 or 20 million years, detonated one after another and blew the neighbourhood clear. The solar system drifted into this cavity somewhere between 5 and 10 million years ago, long after the fireworks, the way a ship glides into a harbour still smelling faintly of smoke. We live inside the scar of dead stars, and we are passing through, not staying. In a few million years our orbit will carry us out the far side. There is even a strange fertility to the scar. The shock waves that carved the bubble piled gas up along its walls, and astronomers have found that nearly all the young stars being born within 1,000 light-years of us today are forming on the bubble's surface, in the compressed rubble of the old explosions. The cavity we are crossing is ringed with nurseries. Destruction on one side of the ledger, birth on the other, and our little raft drifting through the quiet middle of it. One more measurement belongs in this part, because it converts everything above from inference into observation. For most of history, the galaxy's pull on us was a deduction, arithmetic on faith. But the European Gaia spacecraft, which spent a decade measuring the positions of nearly 2 billion stars with almost absurd precision, managed to detect the galaxy's grip directly. As the solar system swings around the galactic centre, our direction of travel bends, and that bending shows up as a coordinated, sky-wide drift in the apparent positions of distant objects. The size of the effect is a bend of a few centimetres per second per year. Centimetres. The instrument caught the Milky Way in the act of steering us, the faintest possible touch on the wheel, measured from a spacecraft the size of a small room. The fall we have been describing all night is not a metaphor. It has been photographed in progress, so here is the vehicle, fully inventoried. A planet spinning at 1,000 kilometers per hour, falling around a star at 30 kilometers per second, which is falling around a galaxy at 230 kilometers per second, bobbing vertically as it goes, currently coasting through a bubble of supernova wreckage, all of it held together and steered by a mass of invisible matter, several times greater than everything visible, and the whole assembly, as the ancient light testified in the last part, travelling at 600 kilometers per second toward a marked point in the southern sky. That is what you, lying still, actually means, spelled out in full. But notice something about the ladder so far. The spin is a circle, the orbit is a circle, even the galactic lap and the vertical bob are loops, closed paths that return. Nothing on the ladder yet is a true journey, a departure without a scheduled return. The 600 km per second drift is the first motion we have found that goes somewhere and does not come back, and everything about its destination is still hidden behind dust. Except that is not quite true. There is one destination on our itinerary that is not hidden at all. It is the first stop on the journey, the nearest thing the universe has to a city on our horizon, and on a dark October night, far from streetlights, you can walk outside and see it with your naked eye. It looks like almost nothing, a faint elongated smudge, easy to dismiss. What it actually is, and what it is in the process of doing to us, took a century of arguments to establish. And the moment astronomers finally settled it, the sky over every autumn for the rest of your life changed its meaning. On any clear, moonless night in October, in the Northern Hemisphere, away from city lights, you can perform a small act of time travel with nothing but your eyes. Find the constellation Cassiopeia, the bright zigzag shaped like a W, and let it point you downward. Just there, if the night is dark enough, you will see a faint, elongated smear of pale light, like a thumbprint on the sky, dim enough that looking slightly to one side of it makes it easier to see. Most people who notice it at all assume it is a wisp of cloud, and then it fails to drift away, night after night, year after year. That smudge is the Andromeda Galaxy. The light entering your eye left it 2.5 million years ago, before our species existed. It is the most distant thing a human being can see unaided, and it is the first destination on the itinerary we have been assembling all night, because that faint thumbprint and the ground you're standing on are falling toward each other right now at about 100 kilometers every second. Even the size of it is a deception. Your eye catches only Andromeda's bright core. The galaxy's full span on our sky is about 3 degrees, 6 full moons laid side by side. If human eyes were sensitive enough to take in its outer disk, Andromeda would be one of the largest single objects in the heavens, a spiral wider than your outstretched thumb, hanging over the autumn horizon. It has been hanging there, growing very slowly larger, through every human lifetime that has ever been lived, and no one knew what it was until about 100 years ago. The argument over its nature was one of the great intellectual fights of astronomy. As early as 1755, the philosopher Immanuel Kant had guessed, on almost no evidence, that the little glowing spirals in telescopes might be island universes, entire star systems like our own Milky Way, seen from immense distances. It was a beautiful idea with no way to test it, and for a century and a half it remained a matter of taste. As late as 1920, serious astronomers were holding formal debates on whether the universe was one galaxy or many, and both sides had respectable evidence. In April of 1920, the National Academy of Sciences in Washington hosted what is remembered simply as the Great Debate. 2 astronomers, Harlow Shapley and Heber Curtis, arguing before their peers over whether the spiral nebulae were small and nearby or entire distant galaxies. Shapley, one of the finest astronomers alive, argued the universe was a single enormous galaxy with the spirals inside it, and much of the evidence available that evening genuinely favoured him. Keep his name in your pocket, by the way. Shapley will return near the end of tonight in a completely different role, holding a photographic plate with something on it that no one would understand for 80 years. The debate itself ended without a knockout. The knockout came 3 years later, and it was delivered in the early 1920s by Edwin Hubble at the huge new telescope on Mount Wilson in California, and he settled it with a species of star. Cepheid variables are stars that pulse, brightening and dimming on a strict schedule, and the schedule gives away their true brightness, which means their distance can be computed from how faint they appear. Hubble found Cepheids inside the Andromeda Nebula, ran the arithmetic, and the answer ended the debate in a single stroke. Andromeda was not a whirl of gas inside our galaxy. It was 2.5 million light-years away, more than 10 times farther than the boldest previous estimates of the universe's entire extent. The cosmos did not grow that day. Our understanding of it detonated. The universe was not a city of stars. It was an ocean of cities. The next obvious question was, is that other city moving? And here the story runs into a problem that sounds trivial, and stubbornly is not. To measure a galaxy's motion along your line of sight, you read the shift in its light, the same physics as the cosmic speed trap from earlier tonight. Light compressed toward the blue if the source approaches, stretched toward the red if it recedes. Simple for a point of light. But Andromeda is not a point. It is enormous on the sky, and it is rotating. Aim your instrument at one edge of the disk and you catch stars swinging toward you on their orbits. Aim at the other edge and you catch stars swinging away. Every patch gives a different answer, and averaging patches fairly, across a target 6 moons wide, defeated instrument after instrument. The number that finally stuck came in 1957 from the Dutch astronomer Hendrik van der Hulst and his colleagues, and it came by radio. Cold hydrogen gas everywhere in a galaxy hums at one precise natural wavelength, 21 centimeters, a single pure note threading through all that rotation. Measure the note's shift across the whole disk, and the rotation averages itself out, leaving the motion of the galaxy as a whole. The verdict: Andromeda's light is blue shifted. It is approaching, at roughly 300 kilometers per second as seen from Earth. Part of that, though, is us. The Sun's own orbit around the Milky Way happens to be swinging us toward Andromeda's side of the sky. Subtract our orbit, and the true closing speed of galaxy upon galaxy comes out near 100 kilometers per second. In the reference frame of the expanding universe, the fairest way to describe it is not that Andromeda is coming here or that we are going there. Both galaxies are falling together toward a point of balance between them. 100 kilometers per second, sustained across 2.5 million light-years. And yet, for 55 more years after Van der Hulst, nobody on Earth knew whether that fall would end in a collision or a passing glance. Here is why. The blue shift measures only the component of motion along our line of sight, the approach. It says nothing about sideways drift. A galaxy sliding diagonally, closing fast but slipping sideways faster, would sail past us at a comfortable distance, 2 ships on crossing courses. To know which future is real, you must measure Andromeda's crawl across the sky, what astronomers call proper motion, and that measurement is brutal. At Andromeda's distance, even a healthy sideways velocity translates to an apparent drift so small that waiting a human lifetime yields a shift thousands of times finer than anything early photography could register. The question did not yield until 2012, when a team led by Sangmo Tony Sohn and Roland van der Merel finished a campaign with the Hubble Space Telescope that amounts to one of the most patient measurements in scientific history. They photographed selected fields of Andromeda's stars, waited 5 to 7 years, photographed them again, and aligned the images against background galaxies hundreds of times more distant, using those as fixed pins in the sky. The stars had drifted. The drift was measured in millionths of a degree. To give that measurement its due, detecting Andromeda's sideways crawl from Earth is comparable to standing in New York and watching a person's hair grow in Los Angeles. It required tracking thousands of stars at once, because no single star could be trusted. Each one has its own private orbit inside Andromeda, and only the average of thousands reveals the motion of the galaxy itself. The result of all that patience was one number, and the number was small. Andromeda's sideways slip is modest compared with its approach, far too modest to carry it past us. The courses do not cross at a distance, they converge. We are going to spend the next part of tonight inside that convergence, watching what actually happens when it arrives, and I will tell you now that almost everything the word collision makes you picture is wrong. But before the mechanics, stay a moment with the simple fact because the sky you can see from your own backyard has an appointment on it now, and it changes what that autumn smudge means. Stand in an open field on a clear night, some 2 billion years from now. The air is warmer. The sun, aging, has already begun to brighten, and Earth is becoming a difficult place. But the night still comes, and the night is no longer ours. Where the faint thumbprint used to sit above the horizon, there is now a structure. Andromeda has grown until it spans a quarter of the visible sky, a tilted disk of pale light, its spiral arms resolved to the naked eye, each arm a highway of hundreds of millions of suns. It does not twinkle. It does not move as you watch. It simply presides. Near the horizon, its outer arm has begun to blur and stretch, pulled subtly out of its curve, the first visible distortion of the approach, and if you knew nothing of astronomy you would still understand in your body that the sky contains something that is coming closer. The light falling on your hands is bright enough to cast the faintest of shadows. There is no sound, and there never will be. Just a second sky rising behind the first, 1 century at a time, with all the patience of gravity. That is the appointment. And there is one more detail from the modern measurements worth carrying into the next part, because it quietly moves the timeline from the future into the present. Galaxies are larger than their visible disks. Both the Milky Way and Andromeda are wrapped in halos of thin, hot gas, invisible to the eye, extending hundreds of thousands of light-years beyond their stars, and recent observations suggest those 2 halos are so large that they may already be in contact. 2.5 million light-years of separation, and the outermost layers are already brushing. By the most generous accounting, the collision is not scheduled. It has started. What remains is only the long, slow arrival of everything else, and the strange physics of what happens when 2 cities of stars attempt to occupy the same harbour. That physics is our next stop, and it begins with a promise that sounds impossible. When the 2 galaxies finally pass through each other, hundreds of billions of stars on each side, the expected number of stars that will actually strike another star is approximately 0. Hold two facts in your mind at the same time and let them refuse to fit together. Fact 1. In a few billion years, two galaxies containing perhaps 1 trillion stars between them will pass directly through each other. Fact 2. The number of stars expected to physically strike another star during that event is, to a very good approximation, 0. Not few, essentially none. The most violent event in our corner of the universe's future is a collision in which almost nothing collides, and understanding how both facts can be true at once is the best way to understand what galaxies actually are. They are not solid objects. They are not even crowds. A galaxy is mostly nothing, a spray of light so thinly scattered that if you shrank the sun to a grain of sand, the nearest neighbouring grain would sit 29 kilometres away. When two such sprays interpenetrate, the stars glide past one another with room to spare, like two swarms of bees passing through the same patch of air, each bee adjusting course, none touching. What collides is everything else, and the everything else is where the story turns out to be genuinely violent, genuinely beautiful, and by the end genuinely sad. Begin with the timeline as the simulations sketch it. For the next 2 billion years or so, not much changes to the eye. Andromeda grows on the sky, autumn by autumn, from thumbprint to structure. Somewhere in that stretch, the mutual pull begins reshaping both galaxies in earnest, and the first instrument of that reshaping is the tide. The same physics that lifts Earth's oceans twice a day operates between galaxies, and on this scale it becomes an instrument of demolition. The side of each galaxy facing the other is pulled harder than the far side, and that difference in pull stretches each disk like taffy. Spiral arms, which have held their lazy curves for billions of years, are peeled away from their galaxies and drawn out into immense streamers that astronomers call tidal tails, arcs of stars and gas tens of thousands of light-years long, flung outward into the dark. Between the two approaching disks, a bridge often forms, a causeway of stars and gas connecting galaxy to galaxy across the closing gap, as if each had reached out a hand toward the other. Every one of those flourishes is made of suns, and many of those suns have planets, and any inhabitants of those planets would look up at a night sky being slowly rearranged, their familiar constellations pulled long like reflections in a warped mirror. The first close passage arrives somewhere around 4 to 5 billion years from now. The two disks sweep through each other at hundreds of kilometres per second, and this is where the bee swarm picture earns its keep. The stars pass, almost every single one. The spacing between stars is so absurdly generous that the two stellar populations thread through each other like two handfuls of sand thrown across a stadium. But star systems do not need to touch to be changed. Gravity reaches. Close encounters, near misses at the scale of light months, twist orbits that had been stable since before Earth existed. The tidy circular traffic of two flat disks dissolves into something tangled, stars looping on wild inclined ellipses, the flat plane of each galaxy thickening, blurring, losing the shape it kept for 10 billion years. Some stars are handed so much energy in these gravitational transactions that they are thrown out entirely, flung from both galaxies into intergalactic space, each one carrying, perhaps, its family of planets with it into a night where the sky holds no stars at all, only the receding glow of the wreckage that expelled them. And while the stars thread past each other untouched, the gas does not. Each galaxy carries billions of solar masses of loose hydrogen spread between its stars, and clouds of gas cannot interpenetrate. They slam. Where the two galaxies' gas reserves meet, the collision compresses them, piles them into shock fronts, and squeezes them past the threshold where gravity takes over and clouds condense into new suns. The result is called a starburst, and the word undersells it. At its peak, the merging pair may forge new stars at hundreds of times, perhaps 1,000 times, the Milky Way's current gentle rate. For a brief era, the wreckage blazes. Millions of newborn stars, the brightest of them blue, white and furious, ignite along the shock fronts, and the merging system, seen from far away, becomes one of the most luminous objects in its region of the universe, a lighthouse announcing the marriage. The first pass is not the end. It is the first swing of a pendulum. The two galaxies sweep past each other, slow, arc back and fall together again, and each cycle is shorter and more destructive than the last, hundreds of millions of years shrinking to tens of millions. until the pendulum runs out and the two systems slump into each other for good. What settles out after several billion years of this is not a spiral. The delicate disk architecture cannot survive such handling. The merged object is a giant elliptical galaxy, a smooth, featureless swarm of stars on chaotic orbits, and astronomers, unable to resist, have already given it a name: Milkomeda. At its very core, one more merger awaits. Each parent galaxy brings its central supermassive black hole to the marriage, ours at about 4 million solar masses, Andromeda's at well over 100 million, and the two sink together through the merged galaxy's heart, spiral around each other, and eventually coalesce in a burst of gravitational waves, ripples in space-time that will spread outward through the universe like the ringing of a struck bell, announcing the completion of the merger to anyone, anywhere, with the instruments to listen. But here is the fate hiding under all that fire, the part the word starburst conceals. Galaxies live on their gas the way a fire lives on fuel. Left alone, a spiral like the Milky Way is a masterpiece of rationing, sipping its reserves slowly enough to keep forming stars for perhaps 100 billion years. The merger torches the savings. The starburst spends, in a few 100 million years, the fuel that two galaxies could have stretched across whole ages of the universe, and when the blaze is over, it is over. The brilliant blue newborn stars are the shortest-lived stars there are. They burn out in a few million years, a cosmic instant, and detonate as supernovas. The merged galaxy, having spent its youth in one extravagant burst, settles into a long retirement it cannot renew. What remains is a slowly reddening swarm, the small, thrifty stars, the orange and red dwarfs that hoard their fuel for hundreds of billions of years. Milkomeda will be enormous, and it will be red, and it will be quiet, an old fire banked down to coals, watching its stars go out one by one, with less and less capacity to light new ones. Stay here for a moment, because this is one of those places where the physics deserves to be felt and not just heard. Every human instinct about catastrophe involves violence you can sense: impact, noise, heat, suddenness. This catastrophe has none of those. No star strikes another star. No planet need be touched. There is no sound because there is nothing to carry sound. A creature standing on a world inside the merger would experience nothing in a lifetime, nothing in 1,000 lifetimes, just a sky that, generation by generation, held more stars in stranger places. The whole cataclysm unfolds at the speed of tides, gently, almost tenderly, two great spirals reaching toward each other, exchanging bridges of stars, circling, merging, flaring once into brilliance, and then dimming forever. Nothing about it is survivable, in the long run, for the kind of galaxies they were, and nothing about it can be felt while it happens. At this scale, tenderness and destruction are the same event, distinguished only by how much time you're given to watch. It is also worth knowing that none of this will be our galaxy's first experience of the process. The Milky Way is a veteran of mergers, and it carries the scars openly, if you know where to look. At this very moment it is in the middle of consuming a small companion, the Sagittarius dwarf galaxy, whose torn remains are wrapped around the entire sky in a stream of stars that loops over the galactic poles. And roughly 10 billion years ago, our galaxy swallowed something much larger, a galaxy whose shredded population still fills the inner halo. Astronomers found its remnants scattered through the Gaia data, like wreckage on a seabed, and named the long-dead intruder Gaia Enceladus. Simulations even suggest a modest chance that during the Andromeda merger, the Sun itself will be swept into one of the tidal tails and carried out into the new galaxy's distant halo. The solar system surviving intact but relocated, left orbiting far above the merged wreckage with a spectator's view of everything that follows. The coming collision is not an aberration. It is simply the largest installment of the process that built every galaxy there is. Honesty requires one more paragraph. Everything above is our best reconstruction, and parts of it have real error bars. The classic simulations put the first passage around 4 billion years from now, and the final merger a billion or two after. But the measurements keep improving, and improvement has brought humility. Andromeda's sideways motion, the neighbour's gravity, especially the tug of the local group's third largest galaxy, the triangulum spiral, and of our own bright satellite, the Large Magellanic Cloud, all shift the choreography, and one prominent analysis published in 2025 feeding the newest data through tens of thousands of simulated futures concluded that the odds of a full merger within the next 10 billion years are close to a coin flip. The fall toward each other is not in question. The blue shift is measured fact. Whether the first pass is a marriage or a long engagement of repeated near approaches remains genuinely open. Astronomy cannot watch a merger happen. The process outlasts civilizations by factors of millions. What astronomy has instead is a photo album of other couples at every stage. The mice galaxies, 290 million light-years away, tails already streaming behind them like their namesakes, ARP 220, 250 million light-years away, photographed by the James Webb Space Telescope in 2023, a merger so far advanced that its great starburst has already ended, leaving only the afterglow of a fire we arrived too late to see lit. Every stage of our own future is hanging in the sky somewhere, happening to someone else. And with that, the first destination on the itinerary is fully mapped. A merger, gentle and total, that ends with our galaxy unrecognizable. But notice what the merger does not answer. Even fused into Milkomeda, even red and quiet, the combined galaxy is still moving, still carried along at 600 kilometers per second toward that marked point behind the southern dust. Andromeda was never the destination. Andromeda is simply the passenger seated closest to us, falling along the same corridor. The corridor itself goes on, far past the merger, towards something that pulls on Milkomeda to be exactly as it pulls on both of its parents tonight. It is time to step back, put every motion we have collected into a single frame, and then follow the corridor outward, to the structure our galaxy actually belongs to, and the current that carries the whole neighborhood. Let us stop climbing for a moment, set the lantern down, and look back at the staircase. You began tonight lying still in a quiet room, and stillness was the first casualty. The floor is moving at 1,000 kilometers per hour around the axis of a planet. The planet is falling around its star at 30 kilometers per second. The star is falling around the center of a galaxy at 230 kilometers per second, bobbing through the disk as it goes, steered by a mass of invisible matter several times heavier than everything that shines. The galaxy is falling toward its nearest great neighbor at about 100 kilometers per second, an approach that ends, sooner or later, in the gentlest catastrophe in the local universe. And beneath all of those motions, carrying every one of them like a current carries the boats on its surface, the ancient light testifies to one more, 600 kilometers per second, 1.4 million miles per hour, toward a marked point behind the dust of the southern sky. Every time tonight we have asked the question, where is everything going, and pinned down an answer, the answer has opened outward onto a larger version of the same question. It happened with the spin, with the orbit, with the galactic lap, with Andromeda. It is about to happen again, and this time the answer stops being an object and becomes an architecture. Here is the pattern hiding under everything we have seen so far, and it is one of the deepest patterns in the universe. Structure comes in ranks, and each rank is a stage of falling. Stars gather into galaxies. That falling finished long ago. Galaxies gather into groups. That falling is happening now, and the Milky Way and Andromeda drawing together is exactly what a group looks like from the inside mid-collapse. Groups gather toward clusters. That falling is well underway, and clusters gather into superclusters, the largest gatherings the universe has attempted, and that falling has barely begun. Rank by rank, from finished to just started, the universe is a construction site where the small rooms were completed first, and the grand halls are still going up. Understanding the traffic in that construction site requires knowing our own address in it, so let us write it out properly. Our galaxy belongs to a modest gathering called the Local Group, a name coined by Edwin Hubble himself in 1936, in the book he wrote after proving other galaxies existed at all. The Local Group is the Milky Way, Andromeda, the smaller triangulum spiral, and somewhere north of 80 dwarf galaxies, faint attendants huddled around the two big spirals like villages around two cities, all of it spread across roughly 10 million light-years. It is bound. Gravity owns it, permanently. Its two cities are falling toward each other, and in the fullness of time, on the order of 100 billion years, essentially everything in the Local Group is expected to drain down into one final object, the merged galaxy we met in the last part, plus its collection of consumed attendants. When you hear the phrase Local Group, hear it as a verdict. This is the set of things that will one day be a single galaxy, the family that shares a single future. Write the whole address out, the way a child writes their address in the front of a schoolbook, and feel how each line changes character. Your street, your city, your country, fixed, as near as matters. Then, third planet, the Sun, 8 light minutes away. Then, the Orion spur of the Milky Way, 26,000 light-years from the galactic centre. Then, the local group, 10 million light-years of family. And here the address stops naming places and starts naming motions. The Sun's line of the address is an orbit. The local group's line is a collapse in progress. And every line we're about to add from here to the end of the video will name a fall that has not finished, which means our address is not really a location at all. It is a trajectory, a description of where we are currently passing through on the way to somewhere else. You do not live at a point in the universe. You live on a slope. But the local group itself is not parked. Roughly 54 million light-years away, in the direction of the constellation Virgo, sits the nearest true metropolis, the Virgo cluster, a swarm of well over 1,000 galaxies packed into a region not much wider than the distance between it and us, all held in a single enormous gravitational well, the whole assembly glowing in X-rays from gas heated to tens of millions of degrees as it falls inward. Clusters like Virgo are the largest structures in the universe that are actually finished, gravitationally speaking, fully formed and bound and simply hungry for more. And the local group, our whole family, is answering the hunger. On top of the Milky Way's private fall toward Andromeda, the entire group is drifting toward Virgo at a few hundred kilometers per second. This motion was set going billions of years ago, and it feeds on itself. As Virgo gathers more galaxies, it grows more massive, and as it grows more massive, it reaches further and pulls harder. The nearby universe is organized like a river basin, and Virgo is one of the low places where the water is pooling. Notice, though, that even Virgo does not account for the number from the ancient light. Our fall toward Virgo is a few hundred kilometers per second in Virgo's direction. Our total motion against the cosmic background is 600 kilometers per second, and it does not point at Virgo. It points well past it, toward that spot on the border of Centaurus and Hydra, far behind the zone of avoidance. Whatever dominates our motion is bigger than the nearest cluster of 1,000 galaxies, and farther, and still hidden. In the 1980s, this became one of the sharpest open questions in cosmology, and the astronomers who cracked it open were a collaboration of 7, spread across institutions on 2 continents, who set out to survey elliptical galaxies across the whole sky and ended up with a nickname that stuck, the 7 Samurai. Their method deserves a sentence of respect, because it is the same trick that powers this entire field. To know whether a galaxy is drifting against the expansion, you need 2 separate numbers: how fast it appears to recede, which is easy, one spectrum gives it to you, and how far away it truly is, which is brutally hard, because distance is the one thing the sky does not print on anything. The 7 Samurai use the internal properties of elliptical galaxies, the relationship between how big they are and how fast their stars churn, to estimate each galaxy's true brightness, and from that its true distance, and from that the recession speed the pure expansion would predict. Any difference between predicted and observed speed is peculiar velocity, the galaxy's private motion, exposed. Do that for one galaxy, and you have a hint wrapped in a large error bar. Do it for hundreds, across the whole sky, and the errors begin to cancel, and what remains is the field itself, the actual pattern of flow in your region of the universe. What they found, published in the years around 1986 and 1987, was flow like grass bent by a wind nobody could feel. The same image Tully and Fisher's maps had hinted at, now stretched across a province. Elliptical galaxies over an enormous sweep of sky. Hundreds of them, across hundreds of millions of light-years, were not sitting in the expansion like raisins in rising dough. They were streaming coherently at several hundred kilometers per second, all leaning toward the same quarter of the heavens, the same quarter our own motion points to. It was the Tully and Fisher result from the beginning of tonight, written 100 times larger. Not a galaxy falling, not a group falling, but an entire province of the universe in migration, and every lane of the migration converging toward one region the surveys could not see into. The 7 Samurai gave the hidden thing its mass estimate, tens of thousands of times the mass of the Milky Way, and the era gave it its name. The Great Attractor stopped being our galaxy's private mystery and became everyone's. The blindness, remember, is geometric, and it is worth feeling how unfair it is. The Milky Way's disk, our own home, viewed from inside, wraps a band of star-clotted dust around the entire sky, and the direction of the Great Migration happens to run almost straight into that band. The 19th century sky mappers called it the zone of avoidance because catalogued nebulae seemed to shun it, and the name outlived the misunderstanding. Nothing avoids that zone. Our house blocks the window. In visible light, something like a fifth of the extragalactic sky is simply gone, curtained off by our own architecture. If the Great Attractor had happened to lie above the galactic pole in the clear, this chapter of astronomy would have been a decade shorter. Instead, the single most influential mass concentration in our corner of the universe sits behind the one curtain we cannot pull down, and astronomy spent the end of the 20th century learning to see through it. With radio waves, which shrug off dust, with infrared light, which slips between the grains, with X-rays, which announce hot cluster gas no matter what stands in front of it. Behind the curtain, slowly, shapes began to resolve. Galaxies, first in dozens, then in thousands, density rising toward a centre, like houses crowding toward a downtown. Something was there, all right, roughly 200 million light-years away, arranged around a core the surveys kept circling closer to. We will walk into that core before the night is over, and we will put a name and a face on the Great Attractor at last. But I want to flag, honestly, where this is heading, because the shape of the discovery is stranger than the discovery itself. When astronomers finally weighed the region behind the curtain, the ledger refused to balance, in a direction nobody wanted, and resolving that imbalance required a set of tools unlike anything else in this story, tools that did not come from astronomy at all. They came from canals in revolutionary France, from plywood factories in the wartime Soviet Union, from the logistics of moving dirt and freight at the lowest possible cost. To follow the current all the way down, cosmology first had to borrow the mathematics of shipping. That detour, from mud to the map of the universe, is the next part of tonight, and it may be the most unlikely story in the whole video. In 1781, a French mathematician named Gaspard Monge published a memoir on what may be the least romantic problem in the history of mathematics: how to move dirt. Armies and engineers of his era were forever digging earth out of one place, the cut, and piling it up in another, the fill, and Monge asked the question a careful quartermaster would ask. Given where the dirt is and where the dirt must go, what assignment of shovelfuls to destinations moves it all at the least total cost? It sounds like a problem you could solve on the back of an envelope, and it is not. It is diabolical. Every shovelful you assign changes which assignments remain sensible for every other shovelful. The problem is a single interlocking whole, and Monge's attempt to tame it planted an equation in the mathematical literature that would grow quietly for 2 centuries, picking up the name of a second Frenchman, André-Marie Ampère, along the way. Hold that image, dirt moving at minimum cost, because tonight it ends with the map of the universe. This is the part of our story where the question, where is everything going, stops being something we wonder about and becomes something we compute. The equation's next great chapter opens in the Soviet Union during the Second World War. Leonid Kantorovich was a mathematical prodigy, a professor by his early 20s, and he had been consulting for a plywood factory when he realized that the factory's scheduling headaches and the wartime problems that soon dwarfed them, moving freight, allocating fuel, routing supplies across a country fighting for its existence, were all versions of one master problem: resources here, needs there, move everything at minimum total cost. Kantorovich generalized Monge's dirt into a full mathematical theory of optimal transport, machinery for finding the cheapest possible rearrangement of anything, and the work was so far ahead of its moment that decades passed before the world caught up. When it did, it brought him the Nobel Prize in Economics in 1975, the only Soviet economist ever to receive one. Mines to factories, farms to cities, dirt to embankments. There is even a wartime legend attached to the mathematics. Kantorovich is said to have applied his optimization methods to the most desperate logistics problem of his city's history: the truck convoys crossing the frozen surface of Lake Ladoga into besieged Leningrad, calculating spacings and loadings for vehicles driving over ice. Whatever the exact details history settles on, the moral survives contact with any skeptic. This is mathematics born of moving real things through a real world at the least possible cost, about as far from the heavens as an equation can live. And the family of ideas it founded turned out to be one of the great universal tools. Today, Optimal transport theory routes freight. Yes, but it also sharpens blurred images, trains artificial intelligence systems, and compares probability distributions in half the sciences, because an astonishing number of questions are secretly the dirt question. Here is one arrangement of stuff. Here is another. What is the cheapest bridge between them? Keep the shape of the idea in view. Stuff, distributed one way, rearranged into another distribution, along the most economical paths possible. Now hold that shape up against the deepest problem in cosmology. The early universe, the one photographed in the ancient light, was almost perfectly smooth. Matter spread nearly evenly everywhere, the same to 1 part in 100,000. The present universe is anything but. Galaxies, groups, clusters, superclusters, great walls around great voids. Between the smooth beginning and the clotted present lies 13.8 billion years of matter on the move, falling, under gravity, from evenness into structure. And gravity is frugal. Matter does not wander. It takes the efficient road downhill, which means the assembly of the cosmos is, in a precise mathematical sense, a Monge problem. The initial distribution, smooth. The final distribution, the universe you see. The question, what paths did everything take, is the dirt question written across the sky. The man who saw cosmology's structure problem clearly enough to make such connections possible was Jim Peebles, and his story deserves a beat of its own. He was born in Winnipeg, Canada, the son of a grain exchange worker and a homemaker, and when he arrived at Princeton and drifted into cosmology in the early 1960s, colleagues might well have offered condolences. Cosmology then was a field with almost no data, a place where careers went quietly to die, more philosophy than physics by the standards of the day. Peebles stayed anyway, and over the following decades he built, piece by piece, the theoretical framework of essentially everything this video has described. How the hot early universe would leave an afterglow, what patterns should be printed on it, how the first faint unevennesses would grow, under gravity, into galaxies and clusters, how the growth of structure could be read as a record of the universe's contents. In 1965, he and his Princeton colleagues were preparing to hunt for the Big Bang's afterglow when word arrived that 2 radio engineers in New Jersey, Arno Penzias and Robert Wilson, had already stumbled onto an inexplicable microwave hiss they could not scrub from their antenna. The Princeton group recognized it instantly for what it was, and the 2 teams published back-to-back, the discoverers who did not know what they had found alongside the theorists who knew exactly what they were looking for. When the Nobel Prize in Physics finally came to Peebles in 2019, it was less for a single discovery than for a lifetime of turning a dead-end field into a precision science. The migration of galaxies that tonight's video traces is, in large part, a story people learned how to tell because Peebles taught them the grammar. And it was in the frameworks he pioneered that the old dirt equation found its way home. Around the turn of this century, mathematicians and cosmologists, among them Roya Mohayai and Andrei Sobolevsky, working with colleagues in France and Russia, showed that the Monge-Ampère-Kantorovich machinery could be run on the real universe. Feed it the observed positions of tens of thousands of galaxies today, add what velocity information we possess, tell it that everything fell here under gravity from an almost smooth start, and the optimal transport solution reconstructs the journey, where each galaxy came from, which paths the matter took, how the current neighborhood assembled itself. It is a crystal ball that runs in both directions. Wind it backward, and you watch the local universe unform, structures dissolving toward the primordial smoothness. Wind it forward and you get forecasts, the probable next positions of everything in the map. The tool has honest limits, and stating them plainly matters. Every step backward in time multiplies the uncertainty, small errors in today's map compounding into large ones far back in the past, and the reconstruction cannot be pushed anywhere near the beginning itself. But within its horizon of validity, the last several billion years, it works, and it has been checked against simulated universes where the true history is known. Mud, freight, galaxies. The same equation, 3 centuries, 1 shape. A crystal ball, though, is only as good as what you feed it, and this is where one more hero of tonight's story rolls up his sleeves. Brent Tully, the same Tully whose 1970s maps first caught the neighbours leaning, spent the following half-century leading the assembly of something unglamorous and priceless: catalogues. The Cosmic Flows program, which Tully and his collaborators have updated edition after edition, is a census of galaxy distances and motions. The fourth edition, released in the 2020s, carries independent distance measurements for tens of thousands of galaxies. Sit with what that means for a moment. Distance, remember, is the number the sky refuses to print, the one that must be pried loose galaxy by galaxy, through pulsing stars, exploding white dwarfs, the churn of stars in ellipticals, the spin of disks. Every entry in that catalogue is a small expedition, years of someone's telescope time and someone's career, and there are tens of thousands of entries. Combine the catalogue with the reconstruction machinery, and the reward is the thing astronomy had never possessed. Not a map of where the galaxies are, but a map of how the universe flows. Streamlines, currents, the actual traffic of the cosmos rendered visible, each galaxy a leaf on a stream whose whole course can finally be traced. Picture what such a map actually looks like, because you have seen its earthly cousins all your life. Take the familiar dotted sky of galaxies and pin to every dot a small arrow, its length the speed of that galaxy's private motion, its direction the direction of the fall. On small scales, the arrows look busy, swirling around local clumps, then step back, and the swirls resolve the way weather resolves on a satellite loop. Arrows over here all feeding a drain, arrows over there all bending around a ridge, whole territories of the sky organised into catchments, as if someone had finally added the wind to a map that had only ever shown the terrain. And the flow maps did something almost embarrassing to a century of astronomy. They revealed that we had been mapping the universe the way a surveyor maps a landscape by moonlight, recording where things stand and missing what the ground is doing. Position had been mistaken for structure. The moment motion itself became the organising principle, the moment you asked not where does everything sit, but where is everything going, the map of our home rearranged itself. Boundaries dissolved. Separate-looking congregations of galaxies turned out to be tributaries of one system. The structure we thought we lived in turned out to be a single limb of something enormous, something with a shape, a boundary, and a heart, none of which anyone had ever drawn before. Our true home structure was discovered not by seeing it, but by watching which way 100,000 galaxies fall. What the falling revealed, the continent of galaxies we actually live in, its name, its 4 great rivers, and the place where all of them drain, is the next part of tonight. And with it comes the audit I promised. The moment astronomers finally weighed the Great Attractor, held the number up against the flow it was supposed to explain, and discovered that the books do not balance, that the thing pulling 100,000 galaxies is itself being pulled by something larger, farther and colder in the dark beyond it. The current, it turns out, has no still water anywhere. Even the lowest water is draining somewhere lower. Somewhere in the mountains of Montana there is a modest ridge of rock where you can stand with 1 foot on either side of an invisible line. Rain that falls on your left boot will run, creek by river, to the Pacific Ocean. Rain that falls on your right boot will end, weeks later and 3,000 kilometers away, in the Gulf of Mexico. 2 raindrops, landing a hand's width apart, are sorted by that ridge into destinies an ocean apart. Geographers call the line a continental divide, and the territory on each side, all the land whose water drains to one sea, a watershed. Hold that ridge in your mind, because in 2014, astronomers discovered that we live inside exactly such a thing, drawn not in rock and rainwater but in galaxies and gravity, and they discovered it by asking the divide's question, not where does everything sit, but which way does everything drain. The supercluster idea itself was old, and it had a long, slightly embarrassing history of being doubted. As far back as 1863, the astronomers William and John Herschel, counting faint nebulae by eye and recording them in handwritten catalogues, noticed an excess of them in the direction of Virgo, a crowding no one could explain. It sat in the catalogues like a clerk's stray tally mark for 90 years. In the 1950s, the French-American astronomer Gerard de Vaucouleurs insisted the crowding was a real structure, a flattened supersystem of galaxy groups with the Virgo cluster near its heart, and he named it the local supergalaxy, later softened to the local supercluster. His colleagues by and large thought he was seeing patterns in noise, a man drawing constellations where there were only scattered dots. He was not. The structure was real, about 100 million light-years of it, 100-odd groups and clusters, our own local group included, arranged in a rough plane, and for 60 years that was the top line of our cosmic address. We lived in the Virgo supercluster. Every textbook said so. Then came the flow maps. In 2014, Brent Tully, with Hélène Courtois, Yehuda Hoffman, and Daniel Pomered, published a new kind of map of the local universe, built from the Cosmic Flows catalogues and the reconstruction machinery of the last part, and with it they proposed retiring the old definition of a supercluster entirely. Forget drawing fences around crowds of galaxies, they argued. Crowding is surface, motion is truth. Define a structure the way a geographer defines a watershed. Take every galaxy's arrow of private motion, trace where it drains, and draw the boundary along the ridgelines, the places where the arrows part company, flowing toward different basins on either side. What emerged from that definition was a continent. The Virgo supercluster, our supposed home, turned out to be one limb of a structure 4 or 5 times larger, a basin of attraction 520 million light-years across, containing the motion of roughly 100,000 galaxies, with the combined mass of about 100 quadrillion suns. All of it, every arrow in the whole enormous catchment drains toward one region. They named the continent Laniakea, a Hawaiian word suggested by a Hawaiian language professor named Nawaa Napoleon, meaning something like immense heaven, chosen to honor the Polynesian navigators who crossed the Pacific by reading stars and currents. It is hard to imagine a better earned name. Laniakea is, precisely, a structure discovered by reading a current. Come stand on the divide itself for a moment. Rise off the map, out of the plane of the galaxies, until whole clusters shrink to bright grains, and position yourself above the boundary of Laniakea, the ridgeline in the dark. Below your left hand, 100,000 galaxies are in motion, and once you know how to see it, the motion is unmistakable. Every grain of light on that side, however it swirls locally, is easing the same way. A snowfall leaning in a wind you cannot feel, sliding down a slope you cannot see, toward a glow near the basin's heart. Below your right hand, just across the invisible ridge, the grains lean the other way, draining toward some other low place beyond the horizon of the map. Galaxies a finger's width from their neighbours, bound for a destination hundreds of millions of light-years apart from theirs. Nothing marks the line. No wall, no gap, no change in the scenery of galaxies. Just 2 rains falling on one roof, parting over the ridge cap, sorted by gravity into different seas. And your own galaxy, if you look for it, is one grain among the 100,000 on the left, well out from the centre, leaning with all the rest. So the address gains its penultimate line. We live in Laniakea, on one of its 4 great limbs, the old Virgo supercluster demoted to a tributary, one river of a 4-river continent, and every river drains to the same place. Follow the arrows inward, down the limb, past Virgo, deeper, and they converge on a region about 220 million light-years from here, buried, of course, behind the zone of avoidance, in the direction the ancient light has been pointing all night. The heart of Laniakea is the Great Attractor, and thanks to the dust-piercing surveys, radio, infrared, X-ray, the heart finally has a face. The deepest well in the basin coincides with a giant cluster of galaxies called the Norma Cluster, catalogue name Able 3627, a crowd several times richer than a typical cluster, glowing in X-rays with the heat of infall, sitting at the bottom of the regional slope like a city at the bottom of a river valley. The destination is not a monster or a void or a tear in space. It is, in the most literal sense, downtown, the largest gathering of matter in our corner of the universe, still actively growing. Point your finger tonight toward the southern constellations Norma and Triangulum Austral, and you are pointing through the dust at the place every galaxy you have ever seen a photograph of is trying to reach. The light arriving from it tonight left 220 million years ago, when the first dinosaurs were finding their feet. One full lap of the sun around the galaxy, one galactic year, spent entirely in transit. And the city is already at work. Telescopes aimed at Norma's outskirts have photographed galaxies falling in and being processed on arrival, their gas stripped off them by the cluster's hot atmosphere in trailing banners 250,000 light-years long, new stars igniting in the torn-away streamers. The destination is digesting the travellers that got there first. Since we have arrived at the heart of the mystery, let us clear away, honestly, the folklore that has grown around it, because if you search for the Great Attractor online, you will meet claims that deserve straight answers. You will read that it is a colossal black hole, dragging the galaxy to its doom. It is not. The flow converges on an extended region of galaxy clusters, mapped in 3 colours of invisible light, and no black hole remotely near the required mass is physically possible, while a fall of 600 kilometers per second spread across 200 million light-years is, for any individual world, the gentlest drift imaginable. You will read that scientists are hiding whatever sits in the zone of avoidance. The opposite is true. The obscuration is our own galaxy's dust. The surveys that pierce it are public, and the maps improve every decade precisely because hundreds of astronomers keep publishing them. The real story, as usual, is stranger than the folklore, and here it is. Because when astronomers finally could weigh the region, cluster by cluster, the audit failed. Norma is enormous, thousands of trillions of suns of matter, dark and luminous together. It is not enough, not remotely. Add up Norma and its whole crowded district, every cluster the dust-piercing surveys have found, and the total pull falls short, by a factor of several, of explaining the speed of the flow pouring toward it. 100,000 galaxies are draining toward a downtown whose gravity cannot account for the traffic, which can only mean one thing, and the flow maps confirm it. The current does not stop at the bottom of our basin. Norma itself is moving. The heart of Laniakea, the deepest point of our watershed, the Great Attractor that pulls the Milky Way and everything around it, is itself falling at hundreds of kilometers per second toward something beyond. The attractor is also attracted. Behind it, 650 million light-years from here, the surveys find the next answer. A wall of galaxy clusters called the Shapley supercluster, the richest concentration of matter in the local universe, dozens of Norma's worth of clusters gathered in one region of sky, discovered, as promised, by the very same Harlow Shapley, who lost the great debate about Andromeda. In 1930, examining photographic plates of the southern sky at Harvard, Shapley recorded a remote cloud of faint nebulosity in Centaurus, noted it as remarkable, and moved on. The plates could not tell him he had found the largest object within 1 billion light-years. 80 years of astronomy later, the flow maps drew their longest arrows and pointed them straight at his cloud. Our basin drains toward Norma. Norma's own arrow points toward Shapley, and given endless time, the mathematics sketches the final itinerary without sentiment. Laniakea condenses toward its heart, and the condensed heart migrates toward Shapley, the watershed itself sliding, whole, into a larger sea. Run the arithmetic on that itinerary, and feel how it comes apart in your hands. 600 kilometers per second sounds like reckless speed, and by every human standard it is. It would cross the United States in about 7 seconds. But at that pace, covering a single light-year takes nearly 5 centuries. The heart of Laniakea lies 220 million light-years away. Even if the destination stood politely still and waited, the trip would take on the order of 100 billion years, 7 times longer than the universe has existed so far. And the destination does not stand still. It is receding down its own slope toward Shapley, which lies 3 times farther yet. Some cosmologists, extending the flow maps outward, have even proposed that Laniakea is not the top of the hierarchy at all, that our whole basin may be one appendage of a still larger catchment, organized around Shapley itself, the divide redrawn one more time, the way every line of our address has been redrawn all night. The regress may genuinely not have ended. Every generation of maps has found the current running farther than the last generation believed. Given endless time, hold on to that phrase because everything now depends on it, and the universe, we will discover, has other plans for the schedule. But before we face the schedule, there is one more force to meet. Everything tonight has pulled. Norma pulls, Shapley pulls, Virgo pulls, Andromeda pulls. When astronomers finished their ledger of pulls, it still did not balance, and the imbalance pointed somewhere no one had thought to look. Not at another crowd of galaxies, but at the emptiest place on the map. Turn around, face away from every destination. It is time to meet the thing behind us. Every map you have ever used has taught you the same quiet lesson. Pay attention to what is there. Cities matter, mountains matter, rivers matter, the blank spaces are just paper. Tonight that lesson fails. Because when astronomers finished adding up everything that is there, every city of galaxies from Virgo to Norma to Shapley, the ledger of our motion still refused to balance. The pulls they could point to, all of them together, could not fully produce the speed and the direction written in the ancient light. Something was missing from the accounting, and it was not another crowd of galaxies hiding behind dust. The missing influence was sitting in the opposite half of the sky, in the blankest region of the map, a place surveys had passed over precisely because there was nothing there to survey. The final force in our story is not a thing, it is an absence, and the absence pushes. The discovery arrived in 2017 from the same school of flow mapping that gave us Laniakea. Yehuda Hoffman, Daniel Pomered, Brent Tully, and Hélène Courtois were doing what the flow maps were built for, reconstructing the full pattern of motion in our cosmic neighbourhood. When they made the map do something new, they let it show not just where the currents converge but where they diverge, not just the drains but the sources. And there it was. On the far side of the sky from the Shapley concentration, several 100 million light-years out, the streamlines all pointed away from a single region, radiating outward from it in every direction, exactly as if the galaxies had been shooed. In that region itself, the surveys found almost nothing, a profound scarcity of galaxies, one of the great voids that honeycomb the universe. They named it the dipole repeller, and the name is a scientific pun of sorts. The dipole is the lopsided pattern our motion prints on the ancient light, and this void, they calculated, is responsible for roughly half of it. Half of our 1.4 million miles per hour is Shapley's side of the sky pulling. The other half is the void behind us, pushing. We are not only being summoned towards something, we are being evicted from somewhere. Now a void cannot actually push. Emptiness has no gravity, no reach, no force to exert, and it is worth being precise about the mechanism, because the truth is more unsettling than a shove. Imagine the universe as a crowd of people walking out of a stadium, everyone drifting apart from everyone else as the concourse widens, which is the expansion we have discussed all night. Gravity is friendship in this crowd. Where people cluster, they link arms and hold together against the general dispersal. A void is a region with no friendships, nothing holding hands, and so there, and only there, the dispersal proceeds at full speed. The void does not throw galaxies away from it. It simply fails to hold them, while every crowded region around its edges does hold them, gathering the borderlands in. The result, for a galaxy at the void's edge, is indistinguishable from a push. Everything drains away from the empty place, not because the emptiness acts, but because the emptiness is the one place where nothing resists the universe's underlying urge to spread. Attractors are where gravity wins, voids are where expansion wins, and we live, it turns out, in the current between one of each, a river with Shapley at its mouth and pure nothing at its spring. Stay with that for a moment, because it deserves to be felt rather than filed away. Everything in your intuition says that motion needs a mover, that if the galaxy is being driven at hundreds of kilometers per second, something with substance must be doing the driving, and for half the effect, there is no something. Turn your mind's eye toward the repeller and try to picture the engine, and the picture fails, because the engine is a place where the universe forgot to put anything. No hidden mass, no dark machinery, no monster in the blank space. Just an absence so large, hundreds of millions of light-years of thinned-out nothing, that its failure to hold us constitutes one of the strongest influences on our fate. Half of the force steering 100,000 galaxies, your body among them, is the gravitational silhouette of nothing at all. It may be the purest lesson the universe has offered tonight. At the largest scales, nothing is not the opposite of force. Nothing is a kind of force, so face it. Turn away from Shapley, away from Norma, away from every glowing destination, and look into the direction we are fleeing. In visible light, the view is almost featureless, a sparse scatter of foreground stars and then depth, deep space with nearly nothing in it. No wall of galaxies, no bright city, just a thinning, an ocean shelf dropping away into genuinely empty water. Nothing there glows for the eye, nothing flares. Instruments, not eyes, are what reveal the strangeness. Chart the galaxies and there are barely any to chart. Trace the flow lines and they all point toward you, streaming out of the emptiness like grass bending away from a place where no wind should be. You're looking at the source of half your speed, and there is nothing to look at. The raft we have ridden all night has a wake, and the wake points back, not to a shore, not to a harbour, but to a hole in the map, a spring of pure expansion, pouring out the one thing voids possess in abundance, room. And notice the quiet miracle of agreement hiding in this result, because it is the reason cosmologists trust the whole picture. The direction of the push from the repeller, the direction of the pull toward Shapley, and the direction of our motion stamped on the ancient light, 3 arrows derived by 3 completely independent methods, from 3 different kinds of data, all line up along a single axis across the sky, to within a few degrees. The speed trap in the oldest light, the census of galaxy distances, and the hunt for the empty places were separate sciences, pursued by separate teams across separate decades, and they converged on one line drawn through the universe, with our galaxy strung on it like a bead, emptiness behind, Shapley ahead, and everything we know sliding between them. When three witnesses who have never met tell the same story in this much detail, the story is true. The repeller settled the local books, but the same era of cosmology produced a stranger claim, and honesty requires we visit it, because it remains one of the most provocative loose threads in the field. In 2008, the NASA astrophysicist Alexander Kashlinsky and his colleagues reported evidence of something far larger than the local flow. Hundreds of galaxy clusters, spread across billions of light years, all streaming coherently at 600 to 1,000 kilometers per second toward one patch of southern sky between Centaurus and Vela. They found it through a subtle trick of light, the tiny imprint that a cluster's hot gas leaves on the ancient background radiation passing through it, which shifts minutely if the cluster is in motion. Kashlinsky called it the dark flow, and the reason the claim electrified people is that a flow so large and so coherent should be impossible. The universe's visible lumps and voids are simply not big enough to generate it. If real, its cause would have to lie beyond the edge of the observable universe itself, some tilt or structure out past everything we can ever see, still tugging on the part we inhabit. Some commentators, going well past the evidence, wondered aloud about the pull of other universes. The measured response came in 2013, when the Planck satellite, mapping the ancient light with the finest precision yet achieved, searched for the dark flow and found no evidence of it. Most cosmologists today side with Planck, and so, honestly, does the weight of the data. But Kashlinsky's team has continued to defend the signal. The debate has never fully closed, and the episode is worth keeping as a reminder of how the repeller story went. The last time the flow maps pointed at something preposterous, the preposterous thing was there. And one more discovery belongs in this part, the newest and perhaps the most haunting, because it says the currents we ride tonight were choreographed before there were stars. In 2023, Brent Tully, the Australian cosmologist Cullen Howlett, and Daniel Pomerade, names you now know, reported that many of the great structures near us, the Sloan Great Wall, the Centre for Astrophysics Great Wall, the Hercules Complex, entire provinces of the cosmic web, are arranged on the surface of a colossal, roughly spherical shell, 1 billion light-years across, centred near the Boötes supercluster. A shell is a strange shape for chance to draw, and they proposed it is no chance at all, but a fossil, a single sound wave. In its first few 100,000 years, remember, the universe was a hot plasma, and pressure waves crashed through it like sound through air. When the plasma cleared, those waves froze mid-ripple, and their crests, regions fractionally denser than average, went on, over billions of years, to gather fractionally more galaxies. Cosmologists have long detected the statistical imprint of those frozen ripples across the whole sky. What Tully and his colleagues claim is far more intimate. One individual ripple, a specific wave that moved through the infant universe, still standing in our sky as architecture, with the great walls of the modern cosmos beaded along its crest. They named it Ho'olelana, from a Hawaiian creation chant, a phrase evoking murmurs of awakening. If they are right, then when you ask why the galaxies around us stand where they stand and flow the way they flow, part of the answer is because of how the universe sounded before it was 380,000 years old. Pulls from the crowded places, pushes from the empty ones, currents older than starlight, and the ghost of a sound wave for a riverbed. The map of where everything is going is finally complete, and every arrow on it agrees with every other, the ancient light, the galaxy surveys, the flow reconstructions, all one compass now, all pointing down the same long slope toward Norma, toward Shapley, toward the deepest basins the universe ever excavated. Which brings us at last to the question that decides the ending of this video. Will anything actually get there? The universe has had 13.8 billion years to run this race. The finish lines have been visible all along, and something we're about to see has been quietly moving them away faster than anything can run. It is time to meet the second invisible hand. In 1917, in an apartment in Berlin, the most celebrated physicist alive sat with his own equations in front of him and refused to believe what they were saying. Albert Einstein had completed general relativity 2 years earlier, and it had already succeeded everywhere he pointed it. The orbit of Mercury, the bending of starlight, gravity itself reimagined as the curvature of space and time. Now he had done the audacious thing and aimed it at everything, applied his equations to the universe as a whole, and the equations had answered with a demand. They insisted that the universe could not stand still. Fill space evenly with matter, and the mathematics offered exactly two behaviors: collapse, everything falling together, or expansion, everything flying apart. A static cosmos, the eternal, unchanging heaven that essentially every astronomer and philosopher of 1917 took for granted, was not on the menu. The equations were, we now know, screaming the truth at their creator. The universe is dynamic. It has a history. It is going somewhere. And their creator flinched. This is the same lesson the epicycles taught at the beginning of tonight, that a mind can hold flawless machinery and still bend it to protect an assumption. Einstein reached into his own masterpiece and added a term it did not need, a fudge factor the mathematics permitted but nothing demanded, a constant, written as the Greek letter lambda, representing a faint outward pressure woven into the fabric of space itself, tuned precisely to hold the universe motionless. He called it the cosmological constant. It was a confession dressed as a correction, and he would come to despise it. 12 years later, Edwin Hubble, the same Hubble who proved Andromeda was a galaxy, demonstrated that the distant galaxies are receding, faster the farther they lie. The universe is expanding, exactly as the unmodified equations had tried to say. The static cosmos died, and lambda's reason for existing died with it. Einstein discarded the constant, and according to the physicist George Gamow, he privately called it the biggest blunder of his life. It is one of history's most instructive regrets, because the blunder was not the constant itself. The blunder was the motive. He had invented a perfectly legitimate piece of physics for a perfectly illegitimate reason, to make the universe hold still, and the universe hold still for no one. But here is the twist that carries us to the end of our story. The constant refused to die. Decades later, the Soviet physicist Yakov Zeldovich noticed something profound about lambda. Quantum mechanics teaches that empty space is not truly empty. The vacuum seethes at the smallest scales, fields trembling, particles flickering in and out of existence, and all that restlessness implies that the vacuum itself carries energy. Zeldovich showed that vacuum energy, if it exists, would behave in Einstein's equations exactly like the cosmological constant, a gentle, uniform, outward pressure inherent in space itself. Lambda was not a fudge factor after all. It was a prediction, waiting for a universe strange enough to need it. That universe announced itself in 1998. Two rival teams of astronomers, racing each other across the world's great telescopes, were measuring the expansion's history using exploding white dwarf stars, supernovas of a type so uniform in brightness that they serve as standard candles across billions of light years. Both teams expected to measure how much the expansion has been slowing, braked by the gravity of everything pulling on everything, the only question being by how much. Both teams, to their own open discomfort, measured the opposite. The distant supernovas were too dim, meaning too far, meaning the expansion has been speeding up, not coasting, accelerating. The two teams, one led by Saul Perlmutter, the other by Brian Schmidt, with Adam Rees doing much of the decisive analysis, checked their results with the special ferocity of rivals who each assumed the other would pounce on any mistake, and when both announced the same impossible answer within months of each other, the rivalry itself became the strongest argument that the answer was real. The discovery earned the three of them the Nobel Prize in Physics in 2011, and it forced cosmology to reinstate, almost overnight, the very term Einstein had disowned. Within a few years, the standard model of the universe had been renamed in its honor. Cosmologists call it Lambda CDM, and the first symbol in the name, leading the whole parade, is Einstein's blunder. Something fills space, uniform and inexhaustible, pushing the expansion faster. We call it dark energy. It is observationally indistinguishable so far from vacuum energy, from lambda itself, and it is not a garnish on the universe. Measure everything that exists, all the matter, dark and luminous, all the radiation, and dark energy outweighs the lot. Roughly 70% of the total contents of the cosmos. Einstein's greatest blunder now leads the standard model of cosmology, and his deepest instinct that space itself might push turned out to be the headline truth about reality. He was wrong only about why. To see how dark energy ends tonight's story, you need only one piece of its logic, and it is vicious in its simplicity. Matter dilutes. Take a box of universe with some galaxies in it, let the box expand, and the same galaxies now rattle in more space. The density falls. But dark energy, being a property of space itself, does not dilute. Every new cubic meter the expansion creates arrives already filled with its allotment of dark energy. Expansion, in other words, manufactures more of the very thing that drives expansion. Matter's team gets no new players, ever, and dark energy's bench is infinite. The game was always going to end one way. For the first several billion years, matter was dense enough to dominate, gravity braked the expansion, and structures assembled themselves in the era of pulls we have spent all night touring. Then, right around 5 billion years ago, as it happens, close to the era our sun was forming, the thinning of matter dropped its density below dark energy's fixed floor, and the universe crossed a line it can never recross. The brakes gave way to a throttle. The expansion began to accelerate, and every year since, dark energy's share of the universe has grown, 70% today, 90% in the far future, then 99%, climbing forever toward everything. And where does the acceleration actually live? We have already been there. The voids. Inside a galaxy, dark energy is utterly outgunned. The local density of matter exceeds the cosmic average by a factor of about 1 million, and gravity rules absolutely, which is why atoms, planets, stars, and galaxies feel no stretching whatsoever. But in the great empty places, where there is no matter to fight back, expansion runs free, and now runs accelerating. The voids are not passive gaps between the action. They are the engine rooms of the universe's future, each one swelling, pressing outward, the dipole repeller and its trillion cousins growing every year, crowding the walls and filaments of the cosmic web between them like rising water crowding sandbars. The web thins, the voids merge. The push we discovered behind us is everywhere, and it is winning. So the universe's final accounting comes down to a single, brutally simple rule, and it is worth stating like the law it is. Whatever gravity has already bound, it keeps. Whatever it has not yet bound, it loses. Bound structures, once fused, once fallen together, are 1,000,000-fold denser than the tide trying to stretch them. They are safe forever. The future mega-galaxy of our local group, safe. The Virgo cluster, already collapsed and cooked and finished, safe, keeping its 1,000 galaxies. But everything larger, every structure still in the process of assembling, every fall still in progress rather than completed, is now racing a deadline. The superclusters are construction projects, remember, the grand halls whose walls were still going up. Laniakea has not fallen together. The great migration toward Norma has 100 billion years left to run, and Norma's own migration toward Shapley longer still, and dark energy took the throttle 5 billion years ago. The mathematics has been done carefully by many groups, and the verdict does not flatter our continent. The expansion between here and the Great Attractor is already opening new space along the route faster than our fall can close it. Laniakea will never condense. Shapley will never receive its watershed. And be careful to picture this correctly, because it is not a chase that the runners are losing. Nothing needs to outrun anything. The galaxies of Laniakea are not fleeing one another through space. The space itself between them is being manufactured, kilometre by new kilometre, along every line between every pair of them. This is also why, farther out, distant galaxies can recede from us faster than light, without breaking any law of physics. The cosmic speed limit applies to motion through space, and those galaxies are barely moving through space at all. The road is stretching beneath them. Our fall toward Norma is a walk down an airport concourse against a moving walkway that runs the other way, and 5 billion years ago someone turned the walkway's speed dial and walked away. For now, momentum still carries us forward against it, but the dial only turns one direction, and there is no hand left on it to turn it back. The word we should have used for our supercluster all along, it turns out, is not structure but attempt. And on the larger scales, the era of attempts, the whole age of falling and gathering and building that turned smooth plasma into galaxies and dinner tables, that era is not merely slowing down, it is over. It ended 5 billion years ago before the Earth was fully formed, and everything since has been momentum. One honest asterisk, because this channel does not deal in false certainty. The verdict above assumes dark energy truly as Einstein's constant, fixed and eternal. In the mid-2020s, a major survey called DESI, measuring the positions of tens of millions of galaxies, reported tentative hints that dark energy's strength may have weakened slightly over cosmic time. The evidence is suggestive, not conclusive, and the community is properly divided. If it holds up, the far future would need redrafting, and cosmologists would face the first genuinely new chapter in the story since 1998. Tonight we tell the standard story, flagged as such. But whichever version nature has chosen, the local truth stands unmoved. The acceleration is measured, the voids are growing, and the journey we have traced all night is being cancelled mile by mile while it happens. Which leaves only the question you came here to have answered, and now, at last, every piece needed to answer it is on the table. Nothing is still, everything is falling, and the falling can never finish. So, truly, finally, where is everything going? At the beginning of tonight, I promised you the answer would come in 3 layers, and that the last layer would not be what you expected. Here is the whole of it, plainly, layer by layer, the complete answer to where everything in the universe is going. The first layer is the near future, and it is the only layer with an arrival. We are going to Andromeda, and Andromeda is coming to us. The fall is measured, the sideways drift is small, and whether the first close pass comes in 4 billion years or 8, whether the marriage is quick or a long engagement of circling approaches, the 2 great spirals of the local group belong to each other, and gravity does not release what it has bound. In the long run, on the order of 100 billion years, everything in our little family, both spirals, the triangulum galaxy, the dozens of dwarfs, drains down into a single enormous aging elliptical galaxy, one red-gold swarm of stars where 200 islands used to sail. That is the first answer, and notice its shape. It is the completed version of everything we watched all night, a fall that finishes. The second layer is the itinerary written in the flow maps, and it is an itinerary of destinations we will never touch. We are going toward Virgo at a few hundred kilometers per second, and we will never arrive. We are going toward the heart of Laniakea, toward the Norma cluster, the Great Attractor itself, the drain of our 100,000 galaxy watershed, and we will never arrive. Norma is going toward Shapley, the deepest basin on any map we have drawn, and it will never arrive. Every arrow on the great map is true. The compass we assembled from ancient light and patient catalogues points exactly where we said it points. The current is real, the raft is really riding it, and the mouth of the river will never be reached because dark energy is lengthening the river faster than the water can flow. The pull we have felt all night, the pull the 1970s discovered and the 7 Samurai chased and the flow maps finally charted, is real force, producing real motion, toward destinations that are being carried away from us faster than we approach them. The attractor is also attracted, and nothing catches anything, all the way up the hierarchy, forever. That phrase we minted at the watershed turns out to be the epitaph of the whole age of structure. Everything reaching, everything receding, a universe of outstretched hands. Pause on the strange comfort buried in the second layer before we take the last step because it rearranges something. All night, the word falling has carried a shadow of menace, the raft in the current, the hidden drain, the summons from behind the dust. But look at what the falling actually built. Every structure in the universe, including the ones reading and narrating this sentence, is a fall that finished. The atoms of your body fell together into a star, were forged, were scattered, fell together again into the sun's little household, fell into a planet, and the planet's fall around its star is the year, and the star's fall around its galaxy is the longest calendar under all the others. Falling is not what threatens the universe's structures. Falling is how the universe makes structures. The menace of tonight was never the current. It is the quiet fact that the current has been switched off at its source, and everything still gliding forward is coasting on the memory of a force that no longer commands the larger scales. And the third layer is the far future, and this is the layer that changes the meaning of the question. Because over the coming hundreds of billions of years, the destinations themselves will leave the sky. As the acceleration compounds, the space between our bound island and every unbound landmark opens faster and faster, until Norma, Shapley, Virgo's stragglers, every glowing city we spent tonight mapping, crosses the horizon beyond which light can no longer make the crossing to us. They will not vanish abruptly. Their images will linger, redshifting, dimming, slowing, like clocks dropped down a well, the light older and older, the news further and further out of date, until the last photons stretch beyond any conceivable instrument. The sky will not go dark all at once. It will go quiet gradually, one landmark at a time, the map unprinting itself in reverse order of distance, farthest first, until the itinerary we trace tonight reads like a list of cities in a country that no longer issues visas. Stand, one last time, in that far future and look up. It is 1 trillion years from now, and you are somewhere in the great merged galaxy, the single island that was once the local group. The night sky above you is, by any human measure, beautiful. Hundreds of billions of stars, most of them small and red and patient, wheeling in a swarm that has long forgotten it was ever two spirals. And that is all there is. There are no other galaxies in this sky. There is no faint thumbprint above any autumn horizon. There is nothing beyond the island but darkness that does not end. An astronomer born under this sky, with instruments finer than anything we possess, would measure the stars' motions and find them orbiting a common centre, would search for the ancient light and find it stretched 1 billion-fold beyond detection, would look for the expansion of the universe and find nothing measurable expanding, no reference point, no flow, no dipole printed on any background, no current, no wake. Every method we use tonight to answer the question would return the same result: no data. That astronomer would conclude, rigorously, carefully, from everything available, that the universe is one galaxy, static, eternal, alone, going nowhere, and that astronomer would be wrong about all of it, and could never, even in principle, discover the mistake. The evidence will have left. We met this pattern at the very beginning of tonight, in the astronomers who read a motionless Earth off a sky that seemed to say so. The universe's last scholars will repeat that ancient error, through no fault of their own, because the sky itself will have stopped telling the truth. Sit with what that means for us, here, tonight. We happen to be alive in the narrow age when the question has an answer, when the ancient light is still warm enough to read, when the galaxies are still close enough to count, when the currents are still visible in the sky like roads on a map. The question, where is everything going, is not eternal. It was born when the first structures began to fall, and it will die when the last landmark slips over the horizon, and the window in which any mind can ask it and be answered is, cosmically speaking, brief. You did not merely learn the answer tonight. You caught the last era in which the answer exists, and after the landmarks are gone, motion itself begins to lose its grip on meaning. The merged galaxy will go on for an extraordinarily long time, trillions upon trillions of years, its red dwarfs hoarding their fuel, its stars slowly scattering one by one as chance gravitational encounters fling them over the island's edge into the dark, where the expansion takes them, each departure permanent. The island evaporates at the pace of forever, and for whatever remains, the old question quietly comes apart in the hands of anyone who tries to hold it. Where is everything going? Toward what? Motion, we learned in the very first hour of tonight, is a relationship. It needs a second thing, a landmark, a witness, a shore. When the last shore is gone, the raft is not moving anymore, not because it stopped, but because moving has run out of things to mean. The ocean we have ridden all night, the current, the watershed, the drains and the springs, all of it smooths away, and what is left is what the water in the glass believed all along: stillness, real, at last, by default. The stillness of a universe that outlived every one of its destinations. If you want a single image to hold all three layers at once, take the one we have carried since the first hour. Our galaxy is a raft on a moonless ocean. The first layer says, there is another raft alongside ours, lashed to us by lines nothing can cut, and one day the two become one vessel. The second layer says, the ocean has a current, the current has a direction, and far downstream there are harbours, lit and real and charted, that the current will never deliver us to because the ocean is widening faster than the current runs. And the third layer says, in the end there is no ocean. The water withdraws beyond every horizon, the harbours go out one by one like lamps, and the raft, still sound, still carrying everything it ever carried, rides at last on a sea so wide and so empty that the word drifting no longer applies to it. The raft outlives the sea. That was always how this story ended from the moment the acceleration was measured. Not shipwreck, not arrival, outliving. So let the answer settle into its final form. the one you can carry to sleep. Where is everything going? Everything is going toward everything else, and it will never get there. The galaxy is falling toward a point in the southern sky it can never reach, pushed by an emptiness it cannot feel, pulled by cities it will never enter, and none of it, not 1 kilometre per second of it, disturbs the surface of the water beside your bed. That is the terrifying truth about where everything in the universe is going. The destination was never a place. It was an age, this age, the brief and unrepeatable era when matter still reached for matter across the dark, and the reaching still meant something, and minds existed to trace the arrows. The reaching will fade, the arrows will soften, the universe will come to rest not by arriving anywhere, but by outliving the very idea of arrival, and it will be calm then, calmer than any night you have ever slept through. But that is not tonight. Tonight the current is still running. Tonight the ancient light still carries our speeding ticket. Andromeda still climbs the autumn sky toward its appointment. The Great Attractor still hauls on its 100,000 galaxies. The great void still presses silently at our backs. And you, lying still in a quiet room, are still travelling at 1.4 million miles per hour down the longest road there is. A road that is growing longer beneath you, faster than anything can travel it. Every motion of the journey is folded into the stillness of your room so completely that the water in the glass beside you does not show one tremble of it. It never has. It never will. The raft rides the current rides the dark, and the dark, for now, is still going somewhere. Sleep well, fellow traveller. The universe will keep falling while you do.